Recording in progress.
Okay, we'll start the lesson. In fact, we'll continue with, we'll start the lesson with, from where we have stopped last time. Okay. So we saw how we find eigenvalues and eigenvectors, and new. Now, sorry, we are there because eigenvectors. Let me recall what we did last time. Huh? Say you have a certain vector. These are the x's, x, y, z. You have a certain transform T. Right? Say this from R3 to R3. So there are three such vectors so that their directions are invariant. TV is something like this. So that means what? TV is simply a scalar multiple of V. But on the other hand, we know that if A is the matrix of transformation, you can go like this. That means what? You can bring this down to this side. Now you can insert an I here. It's okay, right? Because you know I is the identity matrix. Make a medical question. Then you can pull out V, because otherwise you cannot pull out V. If you pull out V, you get A minus lambda. They cannot be, they don't mix with each other. Now there's no problem like that. Now, you know, we want to find V. Non-zero. So we want to find a non-trivial vector. We can non-trivial vector can monahari value vector. So if V is since V is non-zero, you know, from the systems of linear equations, this should be equal to 0. This is called characteristic equation. Now from this, you can find the eigenvalues. I take this as equation 1. Then from 1, you can find the eigenvectors. Then if we arrange those eigenvectors as columns, say there are 3 vectors, you can come up with the matrix P. We saw it last time. And if, I'm not all the time, but if A is symmetric, sometimes we call Hermitian, but let's go for symmetric. Then PTP is I. Means what? P is orthogonal. Orthogonal කියන්නේ මොකද්ද? Orthogonal කියන්නේ මේකේ vectors වලින් orthogonal නෙමෙයි orthonormal basis එකක් set වෙනවා. ඒක තමයි මෙහෙම වෙන්නේ හේතුව. Right? These vectors comprises an orthonormal basis. Here there's a slight abuse of language. Yeah? Okay, now and moreover, now if you multiply this one like P inverse AP, and when it is orthogonal, you know, P inverse is P transpose. So you can write P transpose, which becomes a diagonal matrix. And the funny thing is that, say the eigenvalues are lambda 1, lambda 2, lambda 3, and these are the corresponding eigenvectors. So you get the diagonal form like this. It is always the case. So that's what we did. Now we'll try to see the physical significance of this. ඇයි මේක මේ අපිට වැදගත් වෙන්නේ කියන එක බලමු. ඊට පස්සේ අපිට quadratic forms කරලා අර characteristic equation එකේ පොඩි ටිකක් තියෙන ඒ ටික බලමු. Right? Okay. මේක තමයි අපි කරේ. This is the crux of what we did last time. In fact, this is a culmination point of what we did last time. We did some other stuff as well, but this is the most important part that we did last time. Okay. Now we'll see what the physical significance of this is, right? Okay. We'll start off with a certain transform. Right, just to save some space, I'll use another pen. So if you say this is a transform. Now this transform looks complicated, not very simple. Let me transform it because right. So we want to make this transformation simple. So what we can do is we can use a coordinate transform. First we'll write this as a product of two matrices. So this is what you get. Then you can find the eigenvalues. So let this be A. So you know to find the eigenvalues, this is how you do it, right? You take x is equal to lambda x. Now bring this guy down to the left hand side. Now you can introduce an I. Now you can pull it out. I mean, pull out x from the right hand side. Now, since x is not equal to 0, the determinant is equal to 0. Right? After that, once we have this at our disposal, I'll take this as equation 1. Now I'll write this A. So you have 4 minus lambda because you know what lambda I is. Therefore, you have to subtract lambda from the diagonal. From this, you get I mean, you get some factors like this. Those are what? So you get three values: 4, 5, 2. Those are the eigenvalues. Then you can find the eigenvalues from equation 1. I'll write the eigenvector straight away. With lambda is 2. I mean, you have to do some work here, but we went through one example last time. With lambda is 2. This becomes 2, 1, 1. Okay, you get something like this. When lambda is 4, right? Now, we'll form, these are the eigenvectors. Huh? These are the eigenvalues. These are the eigenvectors. Now, let's form a matrix P. Now, what's our objective? Our objective is to make this one simpler, right? So you arrange these things as columns. Right? Oh boy. Can you see this? You see it? Because you know the pen is not very thick. Guys, can you see it clearly? Probably when I was writing, it might have disturbed you, but now it's okay, I think. How is it? Can you hear me? Is it clear to you? Yes or no? So yes, of course. How is it now? Okay. So should I explain it again, or is that okay? This is the linear transform. So this is a matrix of transform. Then what we did was we tried to find the eigenvalues. So we went through the basic, like we went through from the first principles. So this is what you get. This is a characteristic equation. So you get three eigenvalues. These are the corresponding eigenvectors. Now we can form matrix P. Right? Also note that P transpose P is I. Means P inverse is P transpose. So it is orthogonal. Now we are up to this level, right? Now hereafter this is what we are going to do. Now we come up with a transform. We want to make this look little simpler, right? Okay. Now this is what we do. If it's not clear, please let me know. I used this pen because I don't want to save my space. Otherwise, let me try with another pen. I don't think it will work. Okay. Now these are the eigenvalues and eigenvectors. You know how to find them. Now this is what we do. We want to make this simpler, right? So we come up with some transformation. Now let me write this. This is Tx is Ax. This x. So Tx is equal to Ax. Now I'm going to simplify that. This little better. Now I have formed a matrix P. Now I take X is equal to Py. I'm going to come up with the transformation so that I can make make this look little simpler. It's not going to work. It won't last long. Let me use my regular pen. But if I write it slowly, then I think it's okay. In the place of X, I substitute Py, right? Py X. Now, since T is linear, you can pull it out. You can pull this P out. Right? Now, I want to get rid of this P. So I multiply it by P inverse. Now these two will go away, leaving I there, this Ty, this P inverse AP. Now, if you multiply anything by I can identity matrix again, you get Ty. Now, since P is orthogonal, you can write this as P transpose AP. Now what happens? This is what? This becomes a diagonal matrix. This becomes a diagonal matrix. What's the matrix? Now the first one is 2, second eigenvalue is 4, third eigenvalue is 5. So 2, 4, 5. This is called the diagonalization. The transformation was diagonalized. Now if I want to give this in detail, this is what you have. Now what is this? 2y1, 4y2, 5y3. If you multiply it, this is what you get. Right. Earlier, this is what we had. Earlier, we had this one. Right. So this one is not, I mean, not very simple. So using this transform, we made it simpler. Using the eigen basis. Eigen basis forms, eigen basis is the collection of eigenvectors. There's another thing. I mean, there are some other applications of this as well. So this is how we simplified it into this one. Earlier we had this. Right? Now, before, I mean, later let me explain. Make importance එක මම කියන්න මේක එන වැදගත් සමහර විට. civil engineering වලත් මේක applications තියෙනවා, mechanical වල තියෙනවා, electrical වල තියෙනවා. මේක scale එක බලන්න පොඩ්ඩක් ඉන්න. Right. Now, let me explain you the importance of this. Say, if you take a little piece out of a building, I mean, out of a structure, certain structure, the මොකද building එකකින් පොඩි බිත්තියකින් කැලක් ගන්නවා. බිත්තියක කොන්ක්‍රීට් එකකින් කැලක් ගන්නවා. මේ කැල්ල මේ වගේ තියෙනවා කියලා හිතමු. Little cube. Then we couple ගොඩනැගිල්ල orientation එක අනුව. This may be the east direction, this may be the north direction, this may be heading upward, right? Now there are some stresses. I don't want to explain everything here. This is called sigma xx. Is that clear? Correct. Yeah. We are on this plane x is constant, right? Here to this side y is constant. So from this plane you have sigma yy. From this plane you have sigma zz. These are called normal stresses. And there are some other stresses. They are called shear stresses. There are two shear stresses here on this plane. This way and this way. This is called tau. X is constant. I mean, sorry. This is acting on the plane where x is constant. It is in the direction of z. This acting on a plane where x is constant, but it is heading towards y direction. Likewise, here also there are two stresses. Here also there are two stresses. So you can come up with a 3x3 matrix like this. X. Here, like according to the matrix notation, you have this y. Like x is 1, y is 2, z is 3. Like here tau xy. Tau x z. Then tau y x. Tau y z. Tau zx. Tau zy. Omega theory. This is called stress tensor. So what's the importance of this? Now, from stability, you can show that these two are equal. These two are equal. These two are equal. Then I'll okay. Now this is a little piece obtained from a structure. Building එක ලොකු building එක high rise tower එක වෙන්න පුළුවන්, high rise building එක වෙන්න පුළුවන්, පොඩි කැලක් කඩලා ගන්නවා. Right? Now this is an eigenvalue problem. Wait and see. Then මොකද කරන්නේ? Right? These two guys are equal. This is symmetric. So I mean, by stability, considering stability, you can show that stability can සමතුලිතව සලකලා අර සමානයි කියලා ගත්තා මෙහෙම එකක් කියනවා. මම xy කියලා මේකට දාන්න. මේක tau. Sorry. Tau. ඒක tau. මෙතනත් xy කියලා දාන්න පුළුවන්. මේක මාරු කරලා මේ දෙක සමානයි. Those two are equal. Now These two are also equal. So I will write tau x z instead of zx. Make our matrix notation negative. 1, 1, 1, 2, 1, 3. This row is for x, this row is for y, this is for z. This column is for x, this column is for y, this column is for z. Now, if I write it like this, it is symmetric. Now I take this example. Now, what is the largest stress appearing in this matrix? It is 9. So what happens if you design the building so that it can withstand 9? They can namik stress එක තමයි මේකේ තියෙන ලොකු එක. તો 9ක් දරන්න පුළුවන් වෙන විදිහට හදනවා. එතකොට මොකද වෙන්නේ? එතකොට කෙල වෙනවා. We will be doomed. Why? ඇයි එහෙම වෙන්නේ? We'll see. Now, we obtained the stress tensor using, when we obtained this stress tensor, we choose the axis according to the geometric symmetry. Like that. However, with that setup, this is the stress tensor. Now we are going to choose a certain coordinate transformation. Now we find the eigenvalues of this. You know how to find the eigenvalues now. I don't want to explain. Eigenvalues are 3, 4, 12. The eigenvectors. You see, 2, 1, 6, 3. Therefore, hold on, I have to calculate the eigenvalues, eigenvectors. Okay, 5, 3. Right. These are the eigenvectors. Now, if you take P, now these are bases, eigenbases. These are independent vectors. It is in fact an orthonormal basis. Orthonormal. Each eigenvector, the magnitude of each eigenvector is 1. Also, we can show that PTP is I. That means P is orthogonal. Orthogonal means what? The basis is orthonormal. There's a slight abuse of language here. P inverse is P transpose. Now, with respect to XY Z, this is our matrix. Now we use the coordinate transform. A is transformed to P inverse AP. But you know that P inverse AP is what? P transpose AP. When you take this as P and this as A, I'll take this as A. What is this? You don't have to do a calculation to write the diagonalized 4. What is this? What are the diagonal values you get? What are the diagonal values you get here? In the column, in the diagonal. මෙහෙම ගත්තම මෙහෙමයි දැන් 3 4 12 තමයි අපේ eigen values මේව තමයි eigen vectors, right? So with respect to this basis, these are the values you get in the diagonal. ඉස්සරත් තියෙන 2 4 5 ඉස්සෙල්ලා. Now this is a new stress tensor. Now what are the axes? Now we need to find the axes here. We don't know what they are. what was the transform we considered here? You get P inverse AP when you use this transform. X is Py, right? Now here we are going to find what Y is. Here Y is not clear. What Y, I mean here, what Y, we don't know what Y is. So we need to find what Y is. Right. Okay, if you want to, you can take this down. I'll give you a little time. I gave you two examples, and today the first example I took was the first one I gave you last time. This is a new stress tensor. Early it was like this. If we design this, you design the structure to withstand this stress, it will collapse. Why? Because there's a stress which is equal to 12. Which is equal to 12, right? Now we need to find Y, the new axis, because we need those axes. Y, let me tell you why. Now X is Py. This was a transform we took. Now we need to find Y, because this was a new, now Y willing up to the adult coordinate system here. Right? Okay. Now we'll multiply both sides by P inverse. This I, P inverse can P transpose, because P, this is an orthogonal matrix. I'll give you a name. Now we'll try to figure out what Y is. This is the most important part. Then you can always see the importance of this as well, right? Now P transpose, this P transpose religions means 1 no square root 3 to Himeno, minus name. Iga Himeno. The medical the Pulon common denominator pair on a Pulan to me, make a Kumangim thin square root 3. The x1 minus 6(2) plus 6(3). Run medical gun. The unique Kumangim thin square root 2. Akin minus 6(1) plus 6(2). Make Kumangim thin minus, sorry, 1 no square root 6. Sorry, guys. Methanina x1 plus 6(2) plus 6(3). These are the new axes. Method axes. Then protected anything with the orthogonal transformation, the axis, sorry, orthonormal transform, the axes are rotated. Now, this is what you have now. It's a little hard to draw it. Anyway, I'll try. This is XYZ. So X1, X2, and X3. Now the new coordinate system looks like this. This one is X1 plus X2 plus X3 over square root 3. What is the vector along that direction? I minus j plus k. Direction is square root 3. Another axis is this. These are normal to each other. This y1. So y2. Here, what is the direction? This x1 plus x3. So minus I plus k over square root 2. Sorry. I could have placed it up here. And then the other coordinate axis, probably y3. It is the vector, it is in the direction of this vector, I plus j plus k. It should be a unit vector, right? So square root 3. So it's a new, now these are new x's. But with respect to these x's, right? Now, okay, these are eigenbases, so these are the vectors. You can easily find it since P inverse is P transpose. Now these are the new x's. So what does that mean? This is our new stress tensor. So if you take, with respect to these x's, what happens to shear stresses? Shear stresses go away. Normal stresses are like this, and the 12 is in this direction. So in this direction, we have the largest stress. So when we construct the structure, right, we have to construct it in such a way that it can withstand this larger stress. මේ පැත්තට තියෙනක නවත්තන්න ඕනේ. එතකොට මොකක් හරි මේ පැත්තට විශේෂයෙන් මෙයා වෙන්න එහෙම ක්‍රම තියෙනවා. කම්බි දාද්දි එහෙම තව දාන්න ඕනේ. මේ පැත්තට තියෙන ස්ට්‍රෙස් එක නවත්තන්න. එතකොට බලන්න මේකේ we have no clue. Oh, where's it? Hold on. Then we have no clue. Now, if you find the eigenvalues of this and eigenvectors of this, right? These are the values you get in the final setup. These are called principal stresses. මේවට කියන principal directions කියලා. මේකට කියන principal directions. වැදගත් directions තුන. Stresses තියෙන මෙහෙමයි. මේ පැත්තට තියෙන තුනක්. මේ direction එකේ තියෙන හතරක්. එහෙමනේ ආවෙන්නේ. මේ direction එකේ තියෙන 12ක්. ඕවා තමයි principal stresses. ඒවා තමයි eigen values මේ directions එන්නේ අපිට eigen vectors වලින්. හරි? එහෙම තමයි මේක වෙන්නේ. ඉතින් මොකක් හරි මගේ වැරද්දක් වුණා. මෙතන 1 2 1 තියෙන විතර 2 එකක් කියනවා. calculation එක විතර 2 එකක් කියනවා. මෙතන 2 එකක් කියනවා. මෙතන 2 එකක් කියනවා. මෙතන square root 6 එකක් කියනවා. නමුත් අර ඔක තමයි දැක්කද? eigen values කියන්නේ නිකම්ම මේ mathematical එකක් විතරක් නෙමෙයි. මේක කියන්නේ engineering sense එකක් තියෙනවා. මේක vibration problems වලදී control systems වලදී හැමතැනදීම මේක පාවිච්චි වෙනවා. differential equations වලදී මේවා පාවිච්චි වෙනවා. හරි? right. Then differential equation මොකක්ද පාවිච්චි වෙන්නේ කොහොමද? I'll give a little note here. D operator ගන්නකො D operator කියන්නේ මේක. එතකොට මේතනට අපි දැක්කනේ eigen value එන්නේ මෙහෙමනේ. මෙහෙම එන්නේ. eigen vector එක කියන්නේ මේ x කියන එක. Right, this eigen vector lambda is the eigen value. If I write it like this, df is equal to lambda f. What is f? That is called the eigen function of the D operator. D operator के मुकद्द eigen function निके इन्नी वो मुकद्द f කියන්නේ eigen function निदा मुकद्द එකට ඉන්නේ උත්තරේ e to the power lambda x මේක අවකලනය කරලා මොකක්ද දෙන්නේ බලමු මේක අවකලනය කරලා මොකක්ද දෙන්නේ lambda e to the power lambda x මෙන්න තියෙනවා look at this that is f ඉතින් හිතුව lambda එක කියලා lambda තමයි eigen value එක ඒ වගේ linear operators ඔක්කොටම මෙහෙම එකක් තියෙනවා you always have something like this for every linear operator. That means you apply something, you get the same function. Scalar multiplication is okay. That scalar multiplication is called the eigen value. That this function is called the eigen function. Here they are eigen vectors. Now we'll get into quadratic forms. Our characteristic equation is put together. My idea is to make a several. Quadratic forms is something like this, right? I'll write, I don't want to go for general sense. I will go for this one. My quadratic form, it's like this. You can have x1 squared x2 squared, x3 squared. And thereafter you have x1, x2. You can have make him a degree now. In every term, the degree is 2. Matre dekai. I'll take this as A11, A12, A13. Oh, so this is A22. With the x2, the parak on A33. Make them now 2, A1, A2. Sorry, A12. Make a 2, A23. I'll give you straight away, I'll give you an example. Think about this one. Every term contains a degree 2 polynomial. It will say so. Right? Now I'll okay, forget about this. Huh? Now you do this one. I'll give you a little example. You have to simplify this. I'll give you 2 examples. This 5. Okay. You multiply this. I first multiply this one. You do the second. I do the easy one, you do the difficult one, right? Okay, I first leave this one as it is. I multiply these two first. Okay, how do you multiply? This row with this column. 12x1 plus 2x2. Here 2x1 plus 6x2. Now next time, when you multiply these two, this goes on top of this one. So x1 times 12x1 plus 2x2 plus x2 times 2x1 plus 6x2. What will you get? 12x1 squared. Here you have 6x2 squared. Here you have x1, x2. 2x1, x2, 2x1, x2, 4x1, x2. This is the answer. But there's a connection between these two. When you have this one, you can directly write it like this. How would you do that? Okay. Make x1, x2 giradhan. Write it as a row vector. Write the variables as a column vector. Now you have to form this one. Make it then theoretical positions 1, 1. Maybe theoretical matrix. Make a 1, 1 position. Make a 1, 2. 2, 1, 2, 2. So 1, 1 value in x1, x1. Right? This position is 1, 1. First row, first column. Variables variable 1, 1. You have to multiply the same variable x1 times x1. So x1 times x1 means x1 squared. So its coefficient is 12. Here it is 2, 2. This position is 2, 2. Right? Therefore 2, 2 means x2 times x2. x2 squared. Its coefficient is 6. Look. Here you have 4. But here we have a little problem. This is 1, 2. This is 2, 1. 1, 2 means what? It's a, it should be corresponding to x1, x2. This should be x2, x1. So both x1, x2 and x2, x1 are the same, right? Therefore, their sum should be 4. Here I can put 1, 3. Still you get the same answer. If you multiply this, that you will get the same answer. I can put 1 and 3. Or 0 and 4. Minus 1 and 5. Because it is, I mean, those two numbers add up to 4. Can I with the numbers they got down to Puru? Ekutukarama Hatrapind. Habe, Himudala Vedakna, we meet with the right? We have to be smart. The method numbers they got them on Hatravino, Tamai. If you make a multiply, you get this one. Right? You can even put minus 10, 14. Still you get the same answer. However, if you divide 4 into equal parts, 2 equal parts, 2, 2, him got to put the advantage just, 2, 2. Then this becomes a symmetric matrix. There are a bit of Vasi Gandapulang eigenvalues same way. You advantage the Gandapulang, make it 2 to Ashim. And at the same time, now you can say, you can, without multiplying, you can tell what the answer is. Right? You should have x1 squared, x2 squared, x3 squared, x1, x2, x2, x3, x1, x3. Okay, you tell me the numbers. If you multiply this, what will you get? Which number would you get here? Give the answer. Give me the answer. Usually one person answers, no, everybody should answer. What would you expect? Others? Yes, 5. What about this one? X3 squared. If you multiply this one, what did you get? Here. Right, 5. Correct. What about this number? What about this number? 9. Yes, good. Now, this is a tricky question. What about this number? This one. The coefficient of x1, x2. x1, x2 means 1, 2 positions. This is 1, 2. This 2, 1. 1, 2, 2, 1. Therefore, they are sum. What about this one? 2, 3. x2, x3. 6, because it should be the sum of these two. 2, 3, 3, 2. 6. What about this one? Last one. x1, x3. 2. Yes. Why? Because it should be their sum. Now, it's a simple cakewalk now. Now, if you have a quadratic form like this, we don't know how it behaves. Right? Again, if you have a quadratic form like this, we don't know how it behaves. Even in O levels, we are interested in those type of stuff. Like, say, if you have something like this, for example, in our O levels, x12 plus 2x plus 5. We complete a square like this. Why? Why would you complete a square? Then we can investigate its behavior. Right? We can investigate its behavior. Now, we'll see what we can do with this one. Right. We'll try to complete the squares of this quadratic form. Can you do that? Can you complete the square? I mean, can you write this as a sum of 3 squares? Can you write this as sum of 3 squares? This one? Probably no. Let's try to do this. Okay. Now Q, the quadratic form, can be given like this, right? x1, x2, x3. 5, 9, 5, 3, 3, 3. The symmetric matrix. In general, a quadratic form has this form, this way. I'm like, I'll take this as A, this vector, column vector X. This is its transpose, right? Make it transpose. Now we need a transformation. That transformation, so this is a symmetric matrix. You find the eigenvalues. 3, 4, 12. Eigenvalues, if you take the sum, what is it? 19. What about the sum of these numbers? 19. Trace should be equal to their sum. Now I have a question for you. What is the determinant of this matrix? Can you say what the determinant? Okay, trace is 19. What is the determinant of this matrix? I'm just asking. It is not relevant to this problem. Make it 144. Methune mul product make a determinant. Now the corresponding eigenvectors. Make it what the 2 square root 3 in the full one. These are the eigenvectors. Now you form a matrix. How? Using these as, arranging these as columns. We go to the underflow like this. Now we'll use the transformation. What is it? What is the transformation? X is equal to Py. X is equal to Py. How can you go with this now? Q is okay. We substitute Py. Py transpose A Py. You know, if you take transpose, the direction will be reversed. The direction will be reversed. So it will be like this. Y transpose, P transpose. Something unexpected happened. What about this one? What is that? P transpose AP. Something that we are familiar with. What is it? P transpose AP is that diagonal form. So what does that mean? So what are the expected diagonal values here? Look, these are the eigenvalues. So you get the eigenvalues here. If you multiply, you can multiply them out and still you get this one. So if you want to explicitly write this, that means what? You know the trick now. If it is in this form, how do you write the final answer? This is 3 is corresponding to what? 3 is corresponding to what? It is like the stress tensor, same thing, right? No shear stresses. That means what? No x1, x2, x2, x3s. So what is this? 3 what? 3 times what? You tell me. 3 times what? What should I write here? How do you interpret this as, in the regular quadratic form, how do you write this now? 3 times what? Answer them. Now we are going to expand this. No point of expanding it. Others? You don't understand. So I have to go back and explain. The method, within 12 both 12 in within the 1 position here. You don't answer, therefore I have to assume that you didn't understand. You haven't understood it. What is this? Okay, what would you get? Here. The variable. No, row. Y1 is row. Y1 squared, yes. 3y1 squared, okay. 3y1 squared, yes. Then what about this one? 4y2 squared, 12y3 squared. Now we have a little problem because it was given in terms of x. We have only and make a now this was the given quadratic form. So now it is in terms of y. So if I ask you to write this in terms of x1, x2, and x3, how do you write it? Now this is how you write it. Now this is the transform, right? X is equal to py. Now I want to find y. So if I multiply both sides by the inverse, it will be this. But you know, P is an orthogonal matrix. Therefore, P inverse is P transpose. Okay? Right. Now using this, you can find y. How? Let me show it. Huh? P transpose is this. 1 over square root 3. This is the same as that stress tensor business. It's minus, huh? This is x. Right? Okay. Now, what is y1? You can multiply this, right? Now, x1 plus now, if you multiply this row, this column with this row, you get y1. So y1 is x1 minus x2 plus x3 divided by square root 3. When you multiply it with this one, minus x1 plus x3 divided by square root 2. The last one is x1 plus 2x2 plus x3 divided by the square root of 6. Now, our quadratic form is this, right? 3y1 squared plus 4y2 squared plus 12y3 squared. So this is a complete picture. 3 times. Now you substitute this. Now you can further simplify this if you want to. How do you do that? This square root 3, if you square it, it will be 3. So this will be x1 minus x2 plus x3 squared. This one When you square this, it will be 2. So 1, 2 will go away. This will be 6. So it will go away with this. Right? Now that's how you write the quadratic form as a sum of 3 squares. Okay, did you understand that? Yes or no? Or do you want to, do you need some time to take that down? Now I need everybody to answer. Is there anybody who didn't answer, didn't understand? Can you explain this again? From where? I have to figure out where. Now, if you take this quadratic form, right? Now, this is a quadratic form where in each term you have a degree 2 element. Now, if you try to expand this, what to make expand growth, maybe okay. We're going to pay 1 කියන තැන 12 තියෙනවා 2 2 තියෙන තැන 6 තියෙනවා මේ දෙකේ sum එක 4 කියන එක මෙතනට එනවා. ඒ වගේ මේක expand කරා නම් මේ 1 1 කියන එක 5x1 squared එනවා. මේක පොඩ කරන්න. මේ 5x1 squared මෙතනට එනවා මේ 9x2 squared එනවා 5x3 squared එනවා. මෙතන 3 කිව්වොත් මේ දෙක එකට ගන්න ඕන 6 x1 x2 1 2 10 දෙකනේ 1 2 2 1 මෙතන 1 3 3 1 so ඒක 2 1 3 කියන එකේ 2 x1 x3 here you get 6 x2 x3 so that's how you write the quadratic form in the form of matrices. Now we'll take the same quadratic form, this one. If you have like a quadratic form with 2 variables, it will be a piece of cake. So in general, you can write it like this, right? Let this be x, this be a, this be x transpose, right? So you can find the eigen. Now we are going to do the same thing. To get 3 squares, you need to have numbers here, non-zero numbers here, all the zeros here. So that means a diagonalization is needed. Make a diagonal transformation. You use it, I mean, here for this purpose, you use the eigen transform. Eigen current. Make eigen values so enough. Make a hoynogan, make calling hiwa, make a hand pull over. Makalingana Q1, make a gun of the hiwa. You can say the hand pull. I can swear the hit and currently. You're not make the with you through hand pull. Making eigen vectors through hand pull. The eternal over to the you can find the eigenvectors like this. Then what we do is we want to find the eigenbasis. This is an orthonormal basis. This is an orthogonal matrix. Make a body scene P transpose P can I. It can P inverse can P transpose. Now we right, we go for the transformation. අපි කරන්නේ x equals py කියලා ගන්නවා. py ගත්තා මෙතන මේකට py එනවා මේකට py එනවා. එතන මේක transpose එකදී reverse එකට යන්නේ. yt මුලින් ඉන්නේ pt ඊට පස්සේ එන්නේ. මෙන්න එනවා අපිට අර diagonal මේක. මේක eigen එක ගන්නවා මේක diagonal form එක එනවා කියලා. එන්නේ අර eigen values තුන තමයි ඉන්නේ. හැබැයි මතක තියාගන්න you get the eigen values in the same order. දැන් ඔයගොල්ලෝ මේ දෙක මාරු කරලා තිබ්බනම් 4 3 දෙකත් මාරු වෙනවා. හරියට මේ order එකට තමයි ඉන්නේ. Now, instead of yt, you can write it like this. This is y. When you multiply in the same fashion, then calling again pulwandi. May 1 1 කියන තැන එනවා 3ක්, 2 2 කියන තැන එනවා 4ක්, 3 3 කියන තැන එනවා 12ක්. හරි. ඔය දක්වා හරිද? යහපු දරුවගේ මම අහනවා. Did you understand up to this point? Yes or no? මේක තේරුම් නැත්නම් මට කරන්න දැන් ඒක එක්ස්ප්ලেইন කරන්න බෑ. වෙන මොකක් හරි තේරුම් නැති එකක් තියෙනවද? මොකද මේක ලොං ප්‍රොසෙස් එකක්. ඕකේ. දැන් ඊ හිටියේ නැත්නම් මට ඒකට කරන්න දෙයක් නැති වෙනවා. What about this? Other than that, did you understand the other stuff? Welcome, I mean, the net. Okay. Now, because our purpose is this, make a diagonal decay values to a gun. Because the Hima Tamai, Mewagi terms to not get it, Lian Plum Winnie. Now, now we'll go in the reverse direction because this enough. But if you want to see them, because the x1, x2, x3, if you want to see the quadratic form in terms of x1, x2, and x3, make x1, x2, x3 volume them principal directions using this, you find y. Multiply both sides by P inverse, with the P inverse x, y, we know. P inverse can be transpose because of this, because of the orthogonality. In a Bible to the P transpose 6. Example, you got it. When the P transpose x, y. Because when you come me, make him some square root 3 on a palha to take on 1x1 minus 6, 2 plus 6, 3. Make I multiply the square root through 2 in a method. Through minus 6, 1 plus 0 plus 6, 3. Come with the 10. You give it enough. Then y1 can make, y2 make, y3 make killer than you can within a substitute. Put down a simplify. Now this is equal to what was given earlier. Here you can see the sum of 3 squares appearing clearly. Now you can explain its behavior also. Positive definiteness and stuff like that. Right? Okay. So did you understand this? Okay. Right. Thank you. Thank you so much. Okay. Now, මෙතිනට දුන්න ෆෝම් එකෙම දුන්න විචාර වලින්ම මෙහෙම තමයි අපිට ලියන්න පුළුවන් වෙන්නේ. ස්ක්වයර්ස් තුනක සම් එකක් විදිහට. වෙන විදිහක් නැහැ. ඒකෝට අපිට දැන් පුළුවන් මේකේ තව පොසිටිව් ඩෙෆිනිට්නස්, නෙගටිව් ඩෙෆිනිට්නස් අන්න ඒ ටික පොඩ්ඩක් බලන්න. රයිට්. විනාඩි අපි විනාඩි 5ක් කියලා 10ක් කියලා පටන් ගමු. පොඩි ලක්ෂණ 5ක් කරමු. කොහොමද පුළුවන් කරන්න මේ now we'll see various quadratic forms. Now there are several types of quadratic forms. Now if you take this one we considered just now, the eigenvalues are 3, 4, 12. Therefore you can write it as 3y1 squared, 4y2 squared, y1, y2 and y3 are the functions of x1, x2 and x3. Right. There make a linear functions to nothing. Make a, okay, what's the behavior of this? Make a sum of the squares. Therefore, this always zero. greater than 0 for all x in R3. Is it correct? This is always positive. But there's a little exception. If what happens if all these three are 0? I mean, y1, y2, and y3 are 0. That means except the origin. At the origin, any quadratic form is 0, right? Take this one for example. So that is out of question. When all x1, x2, and x3 are 0, this is just 0. Therefore, when we discuss quadratic, when we investigate the behavior of quadratic equations, we eliminate the origin. Origin එක මේක බිඳුවනේ මූල ලක්ෂයේදී ඔක්කොම බිඳුව වෙන මේක බිඳුව. ඒ ලක්ෂයේදී හැර. Except that point is positive. What about the eigenvalues? Eigenvalues are all positive. Therefore, this is positive. Right? Now we have a special name for that. Now we take the second example. I take Q1, now Q2. Let's take this one. What are the eigenvalues of this? Okay, tell me what are the eigenvalues, what the eigenvalues of this matrix is. I'll give you 10 seconds. So you don't know. But I can write the eigenvalues. 0, 1, 9. Look at the sum. Sum is 10 here. This sum is 10. If you try to find the determinant of this, it will be 0. Your determinant is the product of these three. How did they find the eigenvalues directly? Am I smarter than you? No. Clearly, you guys are smarter than me. What happens is that I have a little trick at my disposal. That's why I could write it like this. I'll tell you how I wrote this later, after finishing this stuff. Right? Okay. Now, if you try to do this, you get 0 y1 squared plus 1 y2 squared plus 9 y3 squared. Now, what can you say about Q? Y1 can be non-zero. Y1 can be non-zero. For example, right? For example, if you try to write this in terms of x1, x2, and x3, you get something like this here. Because we found the eigenvectors earlier. These are the eigenvectors we got, but we get some square root 3 and stuff like that. Anyway, some square root 2, square root 6. Now this is 0. These have non-zero values. Now what happens if these two are 0? If these two are 0, that means x1 is equal to x3. Then this is 0. X1, look, this cannot be negative. Huh? This cannot be negative. But this can be 0. Why? What happens if y2 and y3 are equal to 0? When this is equal to 0 when x1 is equal to x3. This is equal to 0 when x1 plus x2 plus x3 is equal to 0. Since x1 is equal to x3, x2 is minus x3. So if you take points like this This quadratic form is 0. Substitute that -1 + 1, 0. 1 - 2, 1, 0. But this is non-zero. But even though it is non-zero, because of this 0, this whole thing is 0. Again, මේකයි විසඳලා බිඳු වෙන ලක්ෂ ගන්න පුළුවන්. 1 - 2 1 කියන ලක්ෂය කියන්නේ x1 කියන්නේ 1යි, x2 කියන්නේ 2යි, x3 කියන්නේ 1යි නම් if you substitute those, this will be 0. If you substitute these three, this will be 0. Now this is not 0. However, the eigenvalue is 0. Now if one eigenvalue is 0, by making the other two equal to 0, මේව 0 වලට equal කරලා මෙහෙම නෙන්නේ. මම මේක eigenvectors තියෙනවා කියලා ලිව්වා. දැන් මෙහෙම ගන්න ඉන්නේ. eigenvectors අපි කලින් හෙව්වා. ඒවා දැන් ආයෙ මෙතන හොයන්න ඕනේ. මේ quadratic form එක ලිව්වොත් මෙහෙම එන්නේ. මේකත් එක්ක වර්ග වෙන්නේ. -2 නේ. අනේ plus 2 එක ඉන්නේ. 2 එක ඉන්නේ. මෙතන වැරදි. 1 1 1. 1 minus okay. මේකට බලන්න 1 - 1 1 දාන්න බලන්න. 1 - 1 1. x1 කියන්නේ 1, x2 කියන්නේ -1, this is 1. මේක 0 වෙනවා. 1 - 1 1 දැමුත් මෙතන 2 එකක් තියෙනවනේ, මේක 0 වෙනවා. මේක 0 වෙන්නේ නැතිනවනේ, මෙතන 0 එකක් තියෙනවනේ. So this is not the origin. The origin එක නැතුව වෙන point එකදී this becomes 0. Since one eigenvalue is 0. එහෙනම් මේක greater than 0 ම කියන්න බෑ, equal වෙන්න පුළුවන්. sorry, ඒක නමක් තියෙනවා. නම දාලා මේක දාන්න ඕනේ. There's a special name for that. Now I'll get another one. මේක eigenvalues හොයන්න පුළුවන්. So you can write the quadratic form like this. -4y1 squared minus 2y2 squared minus 1y3 squared. Now what can you say about what can you say about the behavior of this Q2? For all, this means for all. Now, since all the values are negative, this should be negative. Now we'll investigate the names of these three. Here, all the eigenvalues are positive, right? And this is also positive. That's called positive definite. You don't have to go through all the process to determine whether it's positive definite. Once you know the eigenvalues, if all the eigenvalues are positive, it's positive definite. Eigenvalues get the Here, what about the eigenvalues? They are either positive or 0. Positive or 0. Right? That means non-negative. Eigenvalues are non-negatives, therefore these also non-negative. 0 or so positive, indefinite. You cannot say definitely it is positive. It's positive indefinite, but it is positive or 0. This can be 0. One eigenvalue is 0, therefore this can be 0. It is based on the eigenvalues. If all the eigenvalues are positive, it's positive definite. If the eigenvalues are positive or zero, it is positive or zero. Means positive indefinite. Positive but not definitely. Anivaryam zero positive zero into pulo. Negative in. What about this one? This negative. This is called negative definite. Sorry, not indefinite. I'm sorry. I mean, positive semi-definite. Bargain. Positive into pulo, somehow zero into pulo, semi-definite. What is semi-definite? Right? Because I haven't taught this for a long time. Probably 18 years. So I have forgotten that name. Right? So it's semi-definite. This negative definite. Now, okay, you take that down. I'll give you a little time. I don't think I have enough time to explain that properties of eigenvalues and how to find Cayley-Hamilton theorem. Not today, possibly tomorrow. You will get simple examples, possibly, right? In the exam, I think you don't get 3 by 3. You might get 2 by 2. Okay, let me go for the next one. After this, let's take 2 by 2 one. You can take 2 by 2 as well, right? This also quadratic form. Here you get eigenvalues as 10 and 0. Therefore, sorry. I put all minus. No. How can I get this? Sum is 0. So this minus 5. No. This way. These two are minus, these two are plus. So sum of the eigenvalues should be negative. Yes. Minus 10, 0. So minus 10 y1 squared plus 0 y2 squared. That's what you get. Now here, okay, what can you say? Q4 is not always negative. Because if y1 is 0, y2 is not 0, that can be 0 still. It's a bindu into pulo. Ika eigenvalue ka bindu nutte bindu into pulo. Make R2. Ika eigenvalue bindu ni damata. We gonna lira pinna nut pulo. Make eigenvalues mehe menni. Rina the height inni. Prinne. Rina the height inni. If x1 is equal, if x1 is equal to x2, this is 0. If x1 is equal to x2, it is 0. Make a multiply minus 5x1 squared minus 5x2 squared plus 10 x1 x2. But x1 is equal to x2 then x1 suman x2 then minus 5 plus 10 minus 20 0. Zero. Negative in almost all the time it is negative, have a 0 in the pulo. Eigenvalues eigenvalues they have මේකට කියන්නේ negative semi-definite. ඒක eigenvalues වලින් කියන්නේ කොහොමද? මම ඔයගොල්ලෝ අහන්න දෙන්න. I'll ask you a question. If the eigenvalues of the quadratic form is 631, what is it? What's the type of the quadratic form? 631. Eigenvalues are 631. All are positive. Then positive definite. If the eigenvalues are -1, -2, -3. Eigenvalues are -1, -2, -3. ඔක්කොම minus. ඔක්කොම negative. So negative definite. If the eigenvalues are 5, 3, 0. 5, 3, 0. If the eigenvalues are 5, 3, 0. Positive semi-definite, right? If the eigenvalues are -2, -1, 0. If the eigenvalues are -2, -1, 0. Negative semi-definite, good. Now the last one. Last one. I am more familiar with this 3 by 3 one, so I'll give you 3 by 3 one. Here, the eigenvalues of this quadratic form. So -1, 1, 2. Now, if you write this, you get -y1 squared plus y2 squared plus y3 squared. If y1 squared is less than these two, it is positive. If this guy is greater, this is negative. So it can be anything. So it's called indefinite. අපිට කියන්න බෑ මොකක්ද කියලා. දන්නේ. No, definitely we can say what it is. Therefore, it is called indefinite. ඒ කියන්නේ eigenvalues positive තියෙනවා negatives තියෙනවා. එහෙම වුණොත් indefinite. Eigenvalues වලින් තමයි ඒක කියන්නේ. නැත්නම් මේකෙන් කියවෙන්නේ behavior එක. Now, the behavior of this quadratic form is determined by the eigenvalues. If eigenvalues are all over, then this is also all over. Like, I mean, all over the place. The plus negative තියෙනවා positive තියෙනවා make it indefinite. ඔක්කොම positive නම් අරකට positive. ඔක්කොම negative නම් ඒකත් negative. Zero thick, like non-zero නම්, sorry, I'm sorry. Non-negative නම්, that means zeros with positives. That's called positive semi-definite. Non-positive නම්, negative and zero නම්, negative semi-definite. ඔය ටික තමයි තියෙන්නේ. ඒක ඔයගොල්ලෝ දන්නව කොහොමද මේක diagonalize කරන්නේ, කොහොමද මේක sum, how do you write it as the sum of 3 squares? ඒ කොහොමද පුළුවන් නේ? Right. ටික හරි. කේලි හැමිල්ටන් එක විතරක් තියෙනවා. ඒක I don't think because I want that I knew that you were going to have a tough time when you encounter the second semester in algebra. That's why I wanted to do give some, I mean, basic idea of those, the nice relationships of each part during the orientation period. එහෙම වුණා නම් ඔයගොල්ලන්ට මාරු ලේසි මේක කරන්න මේ වෙලාවේ. හරි. ඒක ඔයගොල්ලෝ දුන්නේ දැන් මට ඉන්න දැන් මේ වෙලාවේ වෙලා නැහැ අර කියන්න කරන්න. මට මම හිතන්නේ I don't think I have time for that. Because tomorrow we have to go to the faculty early in the morning. I think now I think we'll stop at this point. It's right. I mean, using characteristic equation, you can find the powers of the matrices. But I don't think I have enough time for that. I can do it possibly tomorrow. Tomorrow after 6, I can do it. Probably 1 hour. For 1 hour, I can do it. We'll try to do something like that later. Okay, right. So thank you very much. Uh, so all the best. Tomorrow, I think you have an exam. Do it well, and all the best with your other papers. Okay, then. So I'll see you guys later. And in the second and in the third and the fourth semesters, I teach two complete courses for you and to you guys. Third year differential equation and fourth year vector calculus. It won't be very difficult. Okay, so thank you very much, guys. Good night to all of you.